Okay, so you don't have any theoretical chemistry class. Okay, so yeah, it will be a little bit difficult maybe for you. So yeah, during the practical work, the problem is the practical work will be quite complicated this year. Usually we form groups with 2, 3 or 4 people, and you work on a subject, and together you learn together. However, now it will be splitted, and we'll see how it will be, how we will manage to learn. Okay, so we have an objective of modelization, molecular modelization, and that means that to be able to compute with ab initio methods or quantum chemistry methods the properties of molecules. And what one of the major properties that we want to compute this year is the absorption and emission spectra of molecular materials. That means that we can do some reactivity, but the objective is to be able to do and to be able to calculate the absorption and emission properties. So I will manage all the practical work. That means that usually we have 5 afternoons of practical work where you should have access to the computers. You will launch your calculations with your projects, and you will manage your results, and you do an oral presentation. And Denis Jacquemin, a professor of Nantes University, will briefly present the minimal knowledge of theory. That means that he will briefly rescope what he has done last year in M1, and he will present what is the Schrödinger equation, what are the approximation of the Schrödinger equation, what is an Hartree-Fock method, what is a DFT, what kind of approximation you need to choose, and what are the most reliable, and what you can do for reactivity, what you can do for spectroscopy. And in my part, I will complement this with a practical approach. Okay, so it was the origin of our plan. So the summary is this afternoon we'll talk about what is a computational strategy. That means that once you have a problem, a scientific problem, how you can choose a computational strategy. That means what kind of calculations are needed to answer and discuss your problem. And so it will be today we will start with the publication of Onas Bolton. It's an experimental publication. In a previous mail I asked you to read the publication and to start to think what are the calculations that you could or what kind of information you need with calculations to be able to prove, disprove, and discuss this kind of proposition, scientific proposition. So it's the objective this afternoon. That means that we will talk about a scientific article, we will talk about an hypothesis based on experimental data, and what kind of experimental theoretical data you can produce to compare and discuss such experimental results, and to maybe prove or disprove. Friday you will have another afternoon with me, and you will have just before an afternoon of class with Denis Jacquemin. So you will have half of the theoretical class, and you will best, or at least understand better, what are the kind of theoretical methods that you could use. And Friday we will launch your projects. Okay, so now the question is, do we work in binomes, okay, in groups? That means that, are you able to talk to each other enough to be able to discuss and to make a common project? We have some weeks of calculations, so you can launch quite several molecules, and you can try to have a scientific problem that can be, maybe it's better, but it's not an obligation. If you have a problem that is based on emission properties, that means that you need to calculate the emission properties. That is one of the objectives here in our practical work. But you can also discuss a little bit of absorption properties. You can discuss of fluorescence, phosphorescence properties. That means that maybe there is a problematic is to be able to discriminate between the kind of emission. It can be also a reactivity problem, or maybe a structural problem based on different emissive forms. Okay, so I leave that up to you. Okay, so in a break we can discuss a little bit of that. If you have some ideas, if you already know how to work in binomes or in trinomes, we'll see. But the objective Friday is to be able to launch your calculations. That means that you will produce the inputs, you will give them to me, and I will launch remotely the calculation. I will show you how, and however, this year you will not be in autonomous for this kind of work, because you cannot remotely access the cluster. Okay, one of the advantage of Moltec-Anjou is that you could directly access the cluster, unless unlike in Nantes. However, you don't have the VPN access to do that from your home. Third afternoon, we'll talk about quality control. That means that your first results will come back. Are they correctly converged? Are they okay? What is the quality control in theoretical chemistry? Then we'll discuss the interpretation of your theoretical results. What can you learn from your output files? What can you learn from the answers that are given by the Gaussian, essentially? Okay, and it's a program that will do the computational chemistry work. And how can you extract the data? How can you present your results? How can you confront them to experimental data? Can you directly compare sometimes the data? You need to fully understand what was calculated, okay? And then you can discuss your problem and the limits of your method. That means that here the objective is not to produce specialized theoretical chemists. What we want here is for you that are mainly theoretical experimental students, or you have a polytechnical approach, is to understand what you can expect from calculations, what kind of results and properties simulation you can expect. Maybe to be able to be a little bit autonomous at the start, to define your own computational strategy and to use the problems. But for me is at least to have a critical eye, to be able to discuss with a specialist, to ask him or her some kind of specific questions, and to know if she can really answer your problem. Okay, that means that that's why there is like 3 times more practical approach, where we will discuss launching programs, what is the results, how can you read the results. Okay, it's more a practical approach. In terms of bibliography,
sorry, do I have to see now some picture, or now it's only sound?
No, you have the picture. The stream has begun, so you can connect to my screen, and you will see the picture. You see my name in the list of the people that are connected in the chat, and you can.
Yeah.
Okay, so
I see, but I can only send you a message, but I don't see now like the picture. I only hear the sound.
Please, someone can tell him how you can connect to my screen sharing, because since it's mine screen sharing, you should see somewhere that there is a screen sharing and you can join.
I see only that I am connected to M2 video and sound, but I only hear the sound.
You must click on his username.
I clicked. When I am clicking, it's like to see the profile, maybe.
No,
but
just below my name, you should have something that is called screen sharing or join the stream.
No, I don't see it. It's strange.
Because you're the only one that is not connected in the stream.
Yeah. I see, like when I click to your profile, I see profile, mention, messages, phone, but not video. It's a bit strange.
Do you use the program or the web extension?
Web version.
Okay, so sorry, someone just knocked on the door. I'll be back in 1 minute. So for the bibliography, I can maybe there is more than just these 3 books. Okay, just that if you need some kind of information on the theoretical level, that means what are the theoretical method, what is a molecular orbital, you can use the quantum chemistry of Ira Levine or any quantum chemistry book. Okay, it's this one is a textbook that start from what is expected in first year to the final year. Okay, so there is like what is the Schrödinger equation to what is DFT. The Kramer book, Essential of Computational Chemistry, is more what are the kind of computational approach that you can use, what is molecular modeling, what is dynamical simulations, what kind of DFT methods, what is a basis set, so this is more the practical approach. And since we will be using Gaussian, a program that is quite efficient but not free for molecular modeling, you can use this book, Exploring Chemistry with Electronic Structure Methods, to learn what is a frequency calculation, what is an optimization, what is an excited state, and there is some practical work. I do agree that it sounds strange, since you don't have fully access to this kind of information. Usually I lend those books and I leave them to the Master 2 chamber, or not chamber but classroom, and so yeah, it's quite problematic. But if you find them, if you have access to them or something similar, you have more. There is another thing that is not written by Kramer, but that is Introduction to Computational Chemistry, for example, and it's more or less the same approach. Okay, so this is the kind of bibliography that you can do. I do know that for someone who didn't do theoretical work, who don't know what is a molecular orbital, in 1 month it will be quite harsh to learn and to have all the other classes in the meanwhile. So we will start today with a problem. So let's take a scientific problem, and I've chosen to talk about OLEDs. In 2011, a PhD student of the MIT published a groundbreaking article, Activating Efficient Phosphorescence from Purely Organic Materials by Crystal Design. It's a natural chemistry article, and it was cited in 2018. So it didn't change. Oh, it didn't change, but it's from 2018. So it was already 246 citations. So it's probably more than 400 now. And it was the short article that I proposed to start this class. So you have access in Moodle in the M2 Lumomat space. You have access to the article, and by the way, you have access to the slides of Denis Jacquemin. So I hope that you've downloaded and look at them in advance. Okay, and let's open the article. So it's a natural chemistry article. It's a short communication. Okay, so I will start just by talking about how to read an article. Some of you have never worked on a real bibliography. However, since last year you were confined, you've made more bibliography than most of the M2 students that we've known. When you have an article, you need to start with checking the abstracts, okay, and to be sure that it corresponds to what you're looking for. Then you can just look at the conclusion, for example. Okay, so conclusion starts here, okay, and you see if the result seems really appealing and correspond to what you would expect. And then you look at the iconography, that means the figures. The figures in an article are should be self-explanatory. That means that you can read the figure without looking at the text. That means that you have here a molecule. This is clearly a solid state photo. You have spectroscopic characterization. Here you have a time intensity, so it's a time resolved measure of the emission, and you have an interaction between molecules that is depicted. And you have a more quite important caption that describe precisely the figure. When you will write your reports, you must adopt this kind of approach. That means a figure is not an illustration of a text, it's a presentation of a result, and you can understand the quality of the results, the groundness, the scientific groundness, that if it's reliable or not, just by looking at the picture and looking at the caption. Did you read the article?
Yes.
One yes?
No, 2 yes.
Okay, pas entièrement. Okay, not fully. So, indeed, the thing is that at least if you by the way, if there is something that you could not read, it's the introduction. That means that something that the more difficult part to read in an article is the introduction. The abstract is really condensed, and you sell your article. You say, okay, we've done this and this and this, and we have constated this. Okay, perfect. The introduction is in the scope of the state of the art in this kind of scientific problematics. This is what the other people have done. What is the limit? Okay, what is the problem? And so what is our scientific problem and what we will solve today in this article. So usually 90% of the references of the bibliography are in the introduction, and if you want to do the thing correctly, you should look at each time that there is a reference, what is a reference and what is talking about. So just reading fully one page of introduction can take you hours or even days. If you are not familiar with this kind of problem, that means that if you follow an author and you already know what he has done before and what the others have done, the introduction is not relevant because you know what they are talking about. The introduction is when you want to start to understand why there is this scientific problem. There is like months and years of science to be condensed in some paragraphs. And so the introduction could be almost the last part to read. That means that you will, after reading the figures, you can start with the results. That means that you just forgot what was done before. You try to understand what was done in this article, maybe because your boss told you to read the article. So read the article, read what was done in the article. And when you start to don't understand why they've done this, maybe the answer is in the introduction. Okay? So in an article of 7 pages, if you told me that you didn't fully read it, it's probably because you start with the introduction and it's too much information.
But
And-
actually, for me, introduction was the most interesting part.
Okay,
Because after introduction, I got the full idea, like, why they made it. And actually, it was much easier to understand the graphs and to understand what they make.
okay, so perfect. Here you have two complete approach. Arthur, and not Artem, but Arthur told me that he started to look at the references, so it's got lost in the bibliography. Artem understood the introduction and the problematic science, so he understood better what was the results. So here you have like two different approach, and maybe you will be in between. You don't have the obligation to finish a paragraph. You don't have the obligation to understand each sentences. Okay, you just take it for later. Start, read. What you don't understand, go back to some reference if needed. Okay. So, what is the main problematic here? We have molecules. When you do some molecules, okay, you have some emissions, sometimes not. When you have a material and you pass in a solid state, you create interaction between molecules, and that can drastically change the properties. So in first figure, he studied the para-bromo-benzaldehyde, a really small and cheap molecule. In liquid states, there is a little bit of fluorescence. Okay, and he says that the triplet states, lower in energy, do not have an emissive state because there is a vibrational relaxation. In crystalline state, you have an interaction between the bromine and the oxygen, and this will change the property. You don't have anymore the fluorescence, and you kill some vibronic non-radiative de-excitation path, so there is now a phosphorescence that is observed. And the main project here is that usually for fully organic compounds, the emission is weak. The emission in the solid state is super weak. And usually you need inorganic compounds, okay, or organometallic compounds, and the metal is usually the emissive atom to have the kind of lead. But now you can do some OLED, but many OLEDs are quite complex molecules. Here you have a simple para-bromo-dibenzaldehyde, and if you do a crystal of only para-bromo-benzaldehyde, you see an excimer. That means that there is a dimer de-excitation that kills or limits the phosphorescence. When you dilute, that means when you do a co-crystallization, you have some para-bromo-benzaldehyde in a para-dibromo-benzene, and there is not any more excimers, and you fully observe your phosphorescence. So that was quite groundbreaking. First, it's a cheap molecule. Second, when you have a bromine atom, there is what we call the heavy atom effect. And when we have the heavy atom effect, usually in class, they say that will kill all emission properties. And here, not. And two, with the bromine and the oxygen, there is crystal design, and with the co-crystallization, you have a crystal engineering that enhance your emission properties. So it's great. To be fair, it's not fully the para-bromobenzaldehyde, because there is between layers or between chains, there is some PEG, some large alkyl chains that are chosen to limit the kind of interactions and to force the oxygen-bromine interaction. And there is, like here, you see that there is the absorption in solution, the excitation in dotted, you have the solution emission, and in crystal you have an emission that is not at the same wavelength, or at least you see like two kind of emission, and you have a change in the emission property. What is thought here is that you have some kind of fluorescence, and the phosphorescence being in another state, there is a change in energy, and you have a more green emission. There is an impact on how you do and you form your crystal. If you do a drop cast, that means it's the same as a fast crystallization. You have something that is more like a solution state, but fished in a solid state. And if you leave the crystallization go to a real rearrangement, you have the phosphorescence. Okay. If you do the para-bromo in the co-crystal, in the mixed crystal, you change a little bit the emission, and you have a brighter emission. He has done it with fully alkyl chain, ether chains, and thioether chains. Okay, he has done the same thing with aldehyde. Okay, with both, and he changed the core here with not one benzene but a naphthalene. So by this way, with a molecular engineering approach, he proposed three kinds of emissive compounds with three colors that are different.
Can I ask?
Yeah.
How they knew what substances to use to change the color? Like so they make these modifications, and they like suggested that they will change the color in some way. How they suggested it.
I cannot fully answer this question. That means that there is what they told and what really happened. In Angers, you have a professor that is Pierre Frère that have done quite the same approach in the same period, and it's not a benzene, but it's a thiophene compound. And he looked, and it seemed to be emissive when it was not expected. So I think that the first time that they've experienced this, it's luck. That means that the bromobenzaldehyde was probably a piece of something that was not the final goal. Then there is clearly some chemical engineering, and when they understood what was happening, or think they understood what was happening, they tried to change something. So here you will change the accepting part, and they didn't try. For example, if you put a cyano here, it also works. So they didn't use it because probably it's not the kind of chemistry that they employ in the laboratory. And if they change here the chain, it's because probably they bought the para-bromobenzaldehyde, or maybe it's the same kind of price for the three compounds with the ether, thioether, and so on. And finally, when you in a scientific approach, when you know that you have the chains role, you can change the core, and they think of one kind of permutation, and they probably have seen that there is a naphthalene equivalent, and it was the try. They probably also tried another maybe 3, 4, 5 more things that did not deserve to be presented here. However, here, this paper is super interesting, and there is, and it's really usually the case when you do some spectroscopy, there is quite some hypotheses that are written like it's something like that. Probably, just starting for the first figure, you have Jablonski diagrams, and it is put S and T triplet. In the triplet there is like some energy destabilization. Is it true? In class you've seen that the triplet is many times under the first singlet, and it's not always the case, but it's generally the case. But how can it be sure that there is some kind of energy or intersystem crossing between singlet and triplet? How? Why? Okay, so yeah, it's reasonable, but there is no proof. Here it's fluorescence, here it's called phosphorescence. I suppose that the main reason is the time resolved intensity decrease, but you've maybe seen that you have some kind of delayed fluorescence, and some situations can be more complex than just simple, oh, it is a long time emission, so it's phosphorescence. Here he talks about excimer. How can he be sure? Why? What he can be what he observed is that when you co-crystal, you have a better phosphorescence. Yes, but maybe there is a new interaction. It's not an excimer, and it is an emissive, and it's more intense. You don't know. Okay, so there is enough science to be feasible, realistic, and it's quite there is a chemical soundness, and there is a scientific soundness here. It seems reasonable. The question is, and if we want to do some calculations to prove or disprove this, what can we do? This is the main question here. What kind of calculations do we need to prove or to discuss these results? So usually what I do is that you work in group, okay, and I'll leave it to you some time to discuss this. So what I will do is that I will maybe put I will just up group 1. Oh, okay. Group 2. Group 3. Euh, 5 x 4, 20. 4 x 4, 16. 4 x 4. Okay, perfect. So okay, let's see. I will choose I will select 3 people, and they will stay in the group. you will go in for the others. You will select one of the group. Okay, try to have three equivalent, three group equivalent in size, and you discuss together what kind of calculations you can do, or what information do you need. And maybe for those who are not familiar, just ask, do you think that we can calculate this kind of property, and why? And then we will discuss this. But we will do something that is a world cafe. That means that in 10 minutes you will change of group. That means that half of group 1 minus the ones that are affected to the group 1 will divide and go to group 2 and 3, and you will mix. And the three people that stay in the group must take note for all the people that comes, and you should have it's like a secretary of the reunion. Okay, so Rana, bon. Parti. Donc, okay, so I will say group 1 Rania, group 2 Theo, and group 3 William. Okay, so the other, you will divide yourself in the three groups. Did you understand, Rania? You will be the okay. So divide yourself in the three groups. You select group 1, group 2, and group 3, and you will talk and to see what kind of calculations you need. So, okay, 4 people in each group, please. Et donc, Rania, tu restes dans le groupe 1, et quand ça brasse, tu restes dans le groupe 1, et tu prends note de tout, en fait.
Oui, j'ai compris, c'est juste que quand je vais dans le groupe 1, je vous entendais plus parler.
Ah bah oui. Mais j'essayais de le dire aux gens d'y aller.
Ok. Et monsieur, j'avais une question. Oui. Du coup, on doit discuter sur comment on peut réussir avec la chimie théorique, entre guillemets, et les calculs, à retrouver leur raisonnement ou... Oui. Est-ce qu'on peut essayer de prouver ou d'infirmer ce qui a été proposé expérimentalement? Ok, d'accord. Safia, Majid, Tony, you can, okay. Let's go. Group 2, the second group. Okay, so here in group 2, you can discuss freely with Theo. Theo will take notes, okay, and you can give your opinions, ask your questions of what kind of information you need to prove or disprove this article.
By the way, have you made the DFT report?
Have I done what?
Have you made a DSTC report already? Something very mild.
Bah, t'arrives à avoir une meilleure luminescence en gros de ton composé.
Le moyen qu'on peut utiliser pour calculer.
Alors moi je dirais TDDFT.